Kinematics is most likely my favorite chapter in additional math. It is a discussion about objects in motion, but we need to apply some assumptions to this entire scenario because we are doing math at this level and we don't want it to be too physics. So we're going to be assuming that this object is a particle. A particle means that it is an object that we don't have to consider its mass, okay, and we also don't have to consider its dimension. So it is virtually just a dot, okay. It is a particle that is moving, but it is not like moving in any way that it wants. It is always going to be moving along a straight line. So it is a more restricted kind of motion. So we are basically discussing about a particle that is moving along a straight line. And this is a chapter that is always taught after calculus, which is your differentiation and integration. So we will be needing that. If you are not very familiar with your differentiation or integration, please revisit those two chapters first before coming back to this chapter on kinematics. And but before we try to apply differentiation and integration to deal with this particle in motion, this particle that is moving along a straight line, it is probably better for us to try to discuss about some concepts that is related to, in general, like an object that is in motion. So first, it is going to be this idea of displacement. Displacement, it is a bit like distance, but I will think of displacement as more of like giving us the information about the position of the particle. Because displacement is reference to a point, and it has a positive and negative value, but distance is always going to be positive. So for us to be able to grasp the idea of displacement more, it is probably useful for us to imagine displacement of the particle on a displacement axis. And for displacement, very often in our syllabus, we are using S to represent displacement. So the displacement axis, I'm going to call it this axis, the S axis. So displacement is about this particle with reference to the origin. So I'm going to call the origin O here. So if, for example, I'm going to make use of this example here, okay? So if, for example, we realize that when time is equal to 0, the displacement is -4. So where is the position? Okay, displacement gives us the idea of the position of the particle. So where is the position of this particle along this S-axis? -4. So it is going to be, let's say, somewhere here. This is at -4 displacement. So if I were to just track this particle's motion, we realize that when time is equal to 1, okay, when time is equal to 1, the displacement is equal to 5. So now the position of the particle has shifted to maybe somewhere here when it is at 5. So the particle is, let's say, here. So the particle will be moving, okay, from here, time is equal to 0 all the way until time is equal to 5. And we realize that when time is equal to here, when time is equal to 3, when it is at the third second or minute, okay, when time is equal to 3, the displacement is equal to 2, which means that the particle will make a U-turn. So the particle will U-turn from here and it will stop at 2. So let's say 2 is here, the particle will end here. So this is the full motion of the particle from here to here to here. So for example, if we talk about the displacement here, there will be a negative displacement. If it is here, it is going to be positive displacement, okay, because it is with reference to the S-axis, which was what I've mentioned here. And if you were to see that displacement is equal to 0, that means the position of the particle is exactly at the origin. So displacement, like what I've mentioned, is different from distance, okay? Although they are almost sharing the same, they're almost the same because especially when they share the same units of measurement. So for example, meters, for example, cm. But if you were to look at the motion of this particular particle, what is the distance that this particle has traveled? The displacement was -4, it was 5, then it was 2. But what is the distance that the particle has traveled? Let's try to calculate this. So if we were to try to track the distance that the particle has traveled, it started off at -4, then it moves to 5. So how much has it moved? It will move 4 units, then after that 5 units, so it would have moved 9 units. This is the distance that the particle has traveled. Numerically, I can also try this because we are looking at this with reference to the S-axis. So it can be a 5 minus -4, which will be 5 plus 4. So this will give us the 9. Then after that, the particle is going to make a U-turn, then it's going to come back to here. So what is the distance that the particle has traveled? 3 units. Numerically, this is going to be like 5 minus 2. So we have a 9 plus 3 the distance that the particle has traveled is going to be 12 units. And the next concept that we want to discuss is the velocity. Velocity is like speed, okay, but it is one that comes with a direction. So if, let's say, we are looking at the velocity of the particle and we realize that the velocity is equal to 0. So velocity is the rate of change of the displacement. The rate of change of the displacement of the particle with respect to time. So if v is equal to 0, the particle has no displacement with respect to the change of time, which means that the particle is at rest. The particle is not in motion. But in our additional math, we want to be more specific. Okay, we don't want to say that this particle is like totally at rest, it's not moving at all, because we are always referencing the velocity to time, which means that at that second, v is equal to 0. Which means that it is momentarily at rest. It is experiencing an instantaneous rest. For example, okay, if we were to try to throw a particle, okay, so it's going to move up, then because of gravity, it's going to come back down again, okay, so it is in a straight line motion. So if we were to try to throw a particle, it moves up, then at the maximum possible place, at a maximum possible position above the ground, the particle will make a U-turn and you will just try to fall down again, right? So at a place where it makes a U-turn, you realize that the velocity changes. Okay, what do I mean by the velocity change? Because for velocity, like what I was saying, it has a direction. It is a speed together with a direction. So when it is traveling in the positive x-axis, we can say that the velocity is positive. If it is traveling in the negative x-axis direction, then the velocity is negative. So for this particle, it is, let's say, going up, it's positive. So it's going to be positive velocity. Then after that, it's going to suddenly switch to negative velocity. So at the place where it suddenly switches, it must definitely experience 0, right? Because it went from a positive to negative. So at the place, it is momentarily experiencing a rest, a state where v is equal to 0, and that is what we call an instantaneous rest. Okay, it is a very good phrase to remember because it is tested quite a fair bit in our exams. And that's also, when v is equal to 0, it also implies that the particle is may be experiencing maximum displacement or minimum displacement. Okay, we'll discuss this later when we're trying to look at questions, okay? So, like for example, most likely this place where the particle makes a U-turn, it is experiencing an instantaneous rest. Okay, and one thing that I want you to be clear is it is possible that the particle is at a negative position when s is negative, but it's experiencing a positive velocity. Okay, negative position, positive velocity. So v is positive here. And it is also possible, if you were to look at this same example, when the particle is at a positive position, the displacement is positive too, but the particle is experiencing a negative velocity because it is moving in the negative s direction. Okay, so what I've written here will probably try to help us to recall this. V equal to 0 is when the particle is experiencing instantaneous rest, maximum or minimum displacement. We are going to talk about this maximum minimum later using an example. When it is bigger than 0, particle is moving in the positive direction, positive s direction, but it doesn't imply that it is at a positive position. Okay, it is just moving in a positive direction. Same goes for when v is less than 0, then the particle is moving in the negative direction. If the question were to be asking you for the average velocity from t is equal to 1, from t1 to t2, then you will just look at what is the velocity at t1 and the velocity at t2, then the displacement at t1 and the displacement at t2. Then take S2, let's say S2 is going to be the displacement at T2 minus away S1, which is the displacement at T1, then divided by T2 minus T1. This will give you the average velocity. One last concept about the motion of a particle will be acceleration. Acceleration is the rate of change of the velocity. So if you were to see that the acceleration is 0, that means there's no rate of change of the velocity is not changing, which means that the particle, it can be in motion, okay? A is equal to 0 doesn't mean that the particle is stationary. It just simply means that there's no change in velocity, which means that it could be that the particle is moving, but it's moving at a constant velocity, okay? And when A is bigger than 0, that means I shouldn't be using dv dt now, okay, because I'm going to talk about it later. So in case you are already suspecting that we are going to be using differentiation, yep, we are going to be using that. It's going to be, I'm going to talk about it in a short while, okay? So when A is bigger than 0, it is accelerating. It is accelerating because the velocity is increasing. A is acceleration. A is the rate of change of the velocity. So the velocity is increasing, the particle is picking up speed, the particle is becoming faster and faster. So when A is less than 0, that will mean that the particle is getting slower and slower. It is decelerating. Okay, and if the question were to be asking you for the average acceleration from t1 to t2, time 1 and time 2, then we will just look at the velocity at t1 and the velocity at t2. Let's say here is v1, here is v2, then we will take v2 minus v1 divided by t2 minus t1. This will give us the average acceleration. So how will calculus, how will differentiation and integration comes in? I have a little table here. I think this table is going to be very, very useful to summarize for us how we can be making use of differentiation and integration to relate S, displacement, to V, velocity, and acceleration. Let me just try to draw this little table on the board also. So we are talking about the displacement, S. We are talking about velocity, V, and we're talking about the acceleration, A. So what is V? V is the rate of change of the displacement. Rate of change, we have learned that in differentiation. So if V is the rate of change of the displacement, I just need to take S and we will do a ds dt. This will give us V. We apply differentiation. And what is acceleration? Acceleration is the rate of change of the velocity, which means that we will just take the expression for V, we will differentiate it with respect to t, and this will give us the acceleration, A. And how about integration? Integration is the reverse process of differentiation, which means that if I have the acceleration, we just need to take acceleration and we integrate the acceleration with respect to t. This will give us back the velocity. And if I were to try to reverse the process of differentiation for velocity, I take the velocity, v, and I integrate it with respect to t, it will give me back the displacement. Okay, let's take a look at two questions. This will give us a very good idea how we can be applying calculus, which is differentiation and integration, to kinematics, to particle that is in motion, specifically particle that is moving along a straight line. Let's take a look at questions. So here we have a particle that is moving in a straight line such that its motion is with reference to time, and it has left a fixed point. Okay, and that fixed point that it has left from is O. The displacement is taken to be S, and we're actually given the expression for the displacement with respect to time. It is this that is here. We want to find the value of t when the particle is experiencing an instantaneous rest. When the particle is instantaneously at rest. So we have discussed about it. Instantaneous rest is when v is equal to 0. The velocity is equal to 0. So we need the velocity expression, but what we are given is the expression for the displacement. So in part 1, what we will do is we will take the displacement expression and we will differentiate it with respect to t, because that will help us to get an expression for v, and that is what we want in order for us to discuss about instantaneously at rest. Okay, when the particle is instantaneously at rest. So for displacement, we are given 10 minus 10 over e to the power of t minus 2t. Let's rewrite this. Okay, it's going to be easier for us to differentiate if we were to just rewrite this, especially the second term here, as this 10 minus 10 e to the power of minus t minus 2t. So the velocity will be the rate of change of the displacement ds dt. Differentiating 10, we're going to be getting a 0. Differentiating this, it is going to be minus 10 e to the power of minus t. Applying chain rule to differentiate minus t, is going to be minus 1, then minus 2. So we have a 10 over e to the power of t minus 2. And now we can discuss about instantaneous rest, because we can just simply let the velocity be equal to 0 at instantaneous rest. So when velocity is equal to 0, it will be when 10 over e to the power of t minus 2, this is equal to 0. So from here, 10 over e to the power of t is equal to 2. This tells me that e to the power of t is going to be equal to 10 divided by 2. This is going to be 5. So t is going to be equal to ln 5. And if you were to press this into the calculator to 3 significant figures, it is going to be 1.61. So this is part A. Oops, this is part A. So this is part A, and part B, we want to look at the acceleration. the acceleration when the time is 1.5 seconds. So for part B, acceleration. How do we get acceleration? It is the rate of change of the velocity. So it is a dv dt. We have the expression for v. It is this. Okay, so I'm going to write down v here. V is, okay, let me just rewrite this first term here. Okay, so it's going to be equal to 10 e to the power of minus t minus 2. And now we can find the acceleration because it is the rate of change of the velocity. So I'm going to be differentiating this. It is going to be 10 e to the power of minus t minus 1, differentiating this, which is a constant, it is equal to 0. So this is minus 10 over e to the power of t. So we have this, and now we can find the acceleration when t is equal to 1.5. So when t is equal to 1.5, the acceleration will be minus 10 over e to the power of 1.5. The acceleration here is negative 2.23. Okay, so we know that the particle is actually slowing down because the acceleration is negative. It is experiencing a deceleration. The last part, C, we are looking at the distance that is traveled by the particle in the first 2 seconds. Okay, I'm going to erase B. I will need my result in A, so I'm going to keep it here. So for C, since we are looking at the distance, okay, what we want to do is to sort of have a better idea of the position of the particle. So we're going to try to reference it to the s-axis. And, okay, because the question wants us to find the distance that the particle has traveled in the first 2 seconds. Okay, what you may think of doing is, okay, if it is the first 2 seconds, maybe we should just look at the displacement when t is equal to 0 and the displacement when t is equal to 2, which are easy because we have the expression for s with respect to, s in terms of t. So we can just let t be equal to 0, let t be equal to 2. But this may not be the actual motion of the particle, as in like from here to here. What if the particle, let's say, make a U-turn, like the previous example that we have discussed? So when will the particle make a U-turn? It is most likely at the place where it is experiencing an instantaneous rest. Okay, it may make a U-turn or it may not make a U-turn. We just need to do a check. So we know that this is when the particle experiences an instantaneous rest. That is when t is equal to ln 5 or t is equal to 1.16. And this happens within the first 2 seconds. So we do need to check. So let us do a quick check. Follow me. When t is equal to 0, when the particle first started out, we can see that s is equal to, if I were to make use of the expression for s that is given to us by the question, s is going to be equal to 10 minus 10 over e to the power of 0 minus 2 times 0. So this happened to be equal to 0, 10 minus 10, 10 minus 0. So it happened to be 0, which means that the particle started out at here, the origin. And when t is equal to ln 5, 1.16 seconds, then s is going to be equal to 10 minus 10 over e to the power of ln 5 minus 2 times ln 5. And this, we will be getting a 4.7811. So let's say it is here, 4.7811. So the particle goes here. So from here, the particle will travel to the positive side of the displacement axis because displacement now is positive. So it's going to go to here. And finally, when t is equal to 2, let's check out what is the displacement. Will it be beyond? If it is beyond this 4.781, then the particle didn't make a U-turn. It just happened to make an instantaneous stop at the position, okay? So let's check out. So s is going to be equal to 10 minus 10 over e to the power of t, in this case e to the power of 2 minus 2 times 2, and this is equal to 4.6466. It is smaller than this. So the position of the particle is going to be to the left hand side of this, 4.6466, which means that the particle actually makes a U-turn and come back to here. So what is the total distance that the particle has traveled? Okay, now with this information, with our visualization of how the particle moves along the s-axis, then now we can look at the distance that it has traveled by referencing to this from here to here, what is the distance that the particle has traveled? It is going to be 4.7811 minus 0. In fact, just trying to plot out the position of the particle on the x-axis makes it super simple, because, for example, a line that is like this, I just need to take the s coordinate on the right minus away the s coordinate on the left, then I'll be able to find this. Okay, so we have this, then plus this line here, right minus left, so it's going to be 4.7811 minus away 4.6466. So the total distance that the particle has traveled is 4.92 meters. Let's take a look at another question, question number 2. And in question number 2, we have this particle that starts from rest. It starts from rest. What is the concept that we can use to apply to a particle that is starting from rest? Rest means the particle is not moving at all. That means there's no change of displacement with respect to time. So starts from rest means v is equal to 0. At 5 meters from a fixed point O, so the displacement is 5. V is equal to 0 when t is equal to 0. It moves in a straight line with the velocity. Okay, we are given the expression for the velocity, and time is in seconds after leaving from the initial rest position. Part 1, we are supposed to calculate the acceleration of the particle. We are supposed to calculate the acceleration when the particle is next at rest. That means the particle is going to stop again, so it is when v is equal to 0. Let's try to take a look at when the particle is next at rest. So to look at that at rest, okay, v must be equal to 0. So we are going to let the velocity be equal to 0, and the velocity is this 12t minus 3t squared. This is equal to 0. We can do a quick factorization, which will give us a 4 minus t. This is equal to 0, which means that t is equal to 0 or t is equal to 4. The question asks for next at rest. This was when it was first resting. This was at the place where it started off. The question has already told us it was at rest when it first started off. So this was the beginning. Then after that, this was when it was next at rest, when t is equal to 4. So we are supposed to calculate the acceleration when t is equal to 4. We need the expression for acceleration being expressed in terms of time. So we have the velocity. And how do we get the acceleration from velocity? We will differentiate, because acceleration is the rate of change of the velocity. So acceleration is going to be dv dt. V is this here. So differentiating this, we are going to be getting a 12 minus 3 times 2t. So this is going to be 12 minus 6t. What is the acceleration when it is next at rest? When it is next at rest, it is when t is equal to 4. So the acceleration will be 12 minus 6 times 4. This is equal to minus 12, which means that when it was next at rest, although it is not moving, but the acceleration is minus 12, and it is decelerating. It is actually becoming slower. Next, part 2. Part 2, we are trying to calculate the maximum velocity. Okay, this was the maximum minimum that I was trying to discuss with you guys just now, and we sort of like skipped it. Maximum displacement, maximum velocity, minimum velocity. So we are seeing a question that is like this now. What is the maximum velocity? What was velocity? Velocity was given to us as 12t minus 3t squared. So maximum, minimum, do you find this familiar? Yes, right? Okay, we have learned this in differentiation. So, we don't really have to plot the graph of v versus t, but let's say we were to be sort of like still plotting the graph, okay? So let's say this is v, let's say this is t. Okay, we're just going to do a rough sketch, okay? This graph may not be exactly like this, but we are going to try to imagine for this graph, it is experiencing a maximum point. Maximum v, because the question asks for the maximum velocity. So what is happening at this maximum point? At this maximum point, the gradient must be 0. And since we are talking about a v versus t, that means this is when dv dt is equal to 0. That was what we learned in differentiation under maximum minimum. So we are applying differentiation again. So we're going to just apply exactly what we have learned for that maximum minimum part of differentiation. And to find maximum of v, we will first do a dv dt to try to locate when exactly this is going to happen, t, when v is maximum. So dv dt is going to be equal to 12 minus 3 times 2t. This is equal to 12 minus 60. Hey, isn't that the acceleration? Okay, so if you are able to get it, then it is also possible for you to just let acceleration be equal to 0. But I personally like dv dt better, although they are representing the same thing, but at least this helps me to relate it back to the differentiation application that we have learned. Okay, so I'm going to stick to this, although for some of you, maybe for your schools, you may just be asked to let the acceleration be equal to 0. That is fine too. So we have this. And since we are looking at this point here, okay, that is when the tangent is going to be parallel to the t-axis, we are going to let dv dt to be equal to 0. So letting this be equal to 0, that means 12 minus 6t is equal to 0. So this tells me that t is equal to 2. But just like what we have learned before, when we found that t is equal to 2, it doesn't mean that it is a maximum or minimum yet. Okay, it just means that we have found a place where it is experiencing a stationary point. We need to verify whether it is really a maximum, because the question asks for a maximum. So how are we going to verify this? We have the first derivative or the second derivative test. I think I'm going to use the second derivative test. So we'll do a d squared v dt squared. So I'm going to differentiate this again, which gives us a minus 6. This is easy because this is always less than 0 regardless of t. So when d squared v dt squared is equal to is less than 0, therefore we can say that v is at its maximum. So now we can calculate for the maximum possible velocity. It is going to be when t is equal to 2. So I just need to substitute this back into here. It is going to be 12 times 2 minus 3 times 2 squared. The velocity is equal to 12 meters per second. Now part 3. Part 3, we are supposed to express the displacement in terms of t, the displacement in terms of t. So how do we get the displacement? We need to look at the information that we currently have. We have the expression for the velocity. So we have this. So how do we get back to displacement? We will integrate. Okay, integrating the velocity expression with respect to time get us back to the displacement. So let us try part 3. So in part 3, the displacement is going to be integration of the velocity. So it is going to be integrating. Let's write down the expression for the velocity. It is 12t minus 3t squared. So this is going to be 12. Here we have a t squared over 2 minus 3 times of this is t cubed over 3. And let's not forget about the arbitrary constant, so plus c. So the displacement is going to be equal to 6t squared minus t to the power of 3 plus c. We need to solve for c. So we need to go back to the question to see whether there's any information that helps me to solve for c by trying to find that piece of information that has s and t at the same time. And that is when the question that was when the question mentioned to us that when it is at the position O, the displacement is equal to 5. Okay, the particle starts, so when t is equal to 0, the particle starts at 5 meters from the origin. So we know now that when the particle starts, that is when t is equal to 0, s was 5. So I'm going to substitute this into here, which means that I have a 6 times 0 squared minus 0 to the power 3 plus c is equal to 5. So this tells me that c is equal to 5. And now we have the expression for the displacement. The displacement is going to be equal to 6t squared minus t to the power 3 plus 5. And finally, in part 4, we are once again being asked to find the distance. Okay, not the displacement, but for the distance that the particle has traveled in the first 5 seconds. So let's make sure that we don't just consider 0 seconds and 5 seconds. We want to consider whether the particle makes any U-turn in between. And like what we have mentioned, U-turn usually happens at instantaneous rest. Have we found instantaneous rest? Yes, we have. That was in part 1. In part 1, let me just write down what we have in part 1 in case you guys have forgotten. So in part 1, let me erase this. In part 1, we found that when we let v be equal to 0, instantaneous rest, that is when the velocity is equal to 0. T was 0 or t was 4. Okay, it was either of these two. So we want to check out this. Okay, t is equal to 4 because when t is equal to 0, it was at the beginning. And we know that in the beginning, s was 5. So I can write this down already. When t 0, as the question has already told us, it is 5. And 4 happens within the first 5 seconds. So that's why it's important for us to do the check. So I'm going to check when t was 4 s. Let's try to look at what is the displacement. So it will be 6 times 4 square minus 4 to the power 3 plus 5. The displacement is equal to 37. And let's check out one last position, which is when t is equal to 5, okay? So s is going to be equal to, again using this over here, s is equal to 6 times 5 square minus 5 to the power 3 plus 5. This is equal to 30. So let's now try to plot out the position of the particle, which will help us to better visualize how much it has traveled. So if let's say the origin is here, in the beginning, the particle was here, it was at 5. Okay, then the particle traveled to 37. Let's say here is 37, so the particle went all the way here. Then after that, the particle will end up at 30. So it makes a U-turn coming back to 30. So the particle stops here. The whole motion is going to be like this. So based on this, that we can now visualize, let's see what is the distance. So this line, take the right coordinate minus the left coordinate. So it's going to be 37 minus 5. Then after that, it is this line here, right minus left again. So 37 minus 30. This is equal to 39. Okay, these are two examples that I have for kinematics. There are definitely a lot more interesting examples out there. Let's make sure that we practice this a lot. But for now, this is what I have. And I'm going to see you in the next chapter.